Good morning, everyone. In today's session, we will be evaluating improper integrals using residue integration theorem. Suppose you have integrals of the form minus infinity to infinity f of x dx, where f is a real rational function whose denominator degree is at least 2 units greater than numerator, and f of x is not having any singularities on the real axis. Now, to do this integral, we are going to convert it into a complex integral by replacing x by z, and the curve of integration is the semicircle of radius r along with the line segment from minus r to r. So we can split this integral c f of z dz as integral from minus r to r f of z dz plus integral over the semicircle f of z dz, and we know that by Cauchy's residue theorem this integral is equal to 2 pi I times sum of the residues for the function f of z. Hence integral minus r to r f of z dz is equal to 2 pi I times summation of all the residues of the function f of z inside the curve C minus integral over the semicircle f of z dz. Now, as r tends to infinity, due to the condition that the denominator degree is at least 2 units greater than that of the numerator, the integral over the semicircle will change to 0, and hence from minus r to r, that is minus infinity to infinity, f of z dz is equal to integral minus infinity to infinity f of x dx, and that will be equal to 2 pi I times sum of the residues for the function f of z. Let's do one example. Evaluate the integral minus infinity to infinity x by x square plus 1 into x square plus 4 dx. So we are taking the curve C, and f of z is z by z square plus 1 times z square plus 4 dz. We know that the singularities are at plus or minus I, and z is equal to plus or minus 2i. Hence, we are only calculating residue for the function z by z square plus 1 into z square plus 4 at z equal to I and at z equal to 2i, residue at z equal to 2i. Why? Because as r tends to infinity, we are completely covering the upper half plane, upper half complex plane, and we are only worrying about the singularities inside the upper half plane. So I and 2i are the only singularity lying inside the upper half plane. That's why we are only calculating residue at those points. And we can see that z equal to I and z equal to 2i are simple poles. Hence, the residue is given by limit z tends to I, z minus I times the function z by z square plus 1 into z square plus 4. And that is equal to limit z tends to I, z by z minus I will cancel with the denominator and you are left with z plus I into z square plus 4. And that is equal to I by 2i times minus 1 plus 4, and that is equal to 1 by 6. Same way, we are calculating the residue for the function z by z square plus 1 times z square plus 4 at the point z equal to 2i, that is a second singularity lying in the upper half plane, that is equal to limit z tends to 2i z minus 2i times z by z square plus 1 times z square plus 4. And that is equal to limit z tends to 2i z by z square plus 1 times z minus 2i will cancel with both denominator and numerator, and you are left with z plus 2i, and that is equal to 2i by 2i the whole square is minus 4 plus 1 times 4, and that is equal to minus 1 by 6. Hence, this integral value is equal to 2 pi I time sum of the residue at z equal to I and 2i, and that is 1 by 6 minus 1 by 6, and that is equal to 0. Hence, this integral minus infinity to infinity x by x square plus 1 times x square plus 4 dx is equal to 0. That's how we are converting the real improper integral into a complex integral and evaluating it using residue integration theorem. Thank you.